Welcome back to ECE 320A. What I want to do in this session is to briefly go over the course in a whole, or do a course overview, and in particular the textbook that we will be using, which is the 10th edition of Nielsen and Rydell. We'll be covering the second half of that textbook in 320A, more specifically chapters 10 through 15. Then we'll skip over the Fourier material and jump into two-port material in chapter 18. In between or during that time, we'll talk about Appendix E material, which is frequency response and Bode plots. And if time permits, we will go in and pick up some of the Fourier material in the form of Fourier Series in chapter 16. In terms of a course overview, we're really starting at where the earlier class left off, which was chapter 9 of Nielsen and Rydell, and that was dealing with sinusoidal steady state analysis. What we want to do now is carry that a little bit further and to talk about power. And there are many different ways of talking about power. Maybe the first idea to come to mind is this product of voltage and current, and if we do that at each instant of time, if we take V of t times I of t, that now gives us the instantaneous power of a system. And that's really sort of where we start in terms of thinking. And that's what we are doing in chapter 10, is we're beginning to think about instantaneous power, but in fact, we're dealing with a particular scenario, which is instead of having to worry about the power at each instant of time, we're dealing in a steady state sinusoidal setting, or we're looking at a frequency of 60 hertz. We're operating in a steady state frequency domain setting, or in a sinusoidal steady state setting. And because of that, maybe there's a cleaner way we can maybe talk not in terms of keeping track of what's going on at each instant of time, but maybe we can now think about what's happening on average, or what is the real power, and that's in terms of watts, or has units of watts, and that's what energy or work we are actually doing per unit time. And energy per time is then power, and that's where we get this P. And the source in this case is essentially going to be saying what needs to be supplied to the load. So in terms of power now in chapter 10, we'll be dealing with sources, we'll be dealing with loads. The loads are how much power do we need to operate effectively. And again, we're dealing with this energy per unit of time, and we're talking now about average power. And when we're talking about average power in watts, that's what work is being done per unit of time. But unfortunately, or fortunately, since we want to be employed, the world's a little bit more complex than just pure resistors. That would actually be too easy. And what we really have is, when we get into a system, we may have a distributed collection of inductance and capacitance. We won't look at the distributed nature so much, as we'll lump those up into discrete elements, and we'll now deal with inductors and capacitors in addition to resistors. And because we now have these inductors and capacitors, these are energy storage devices, and because of that, we're now worrying about storing energy in the magnetic field and then releasing it back to the system, pulling it in, releasing, pulling in. So we're fluctuating the magnetic field, and with capacitors we have this same concept, is we are now exchanging energy between the electric field and the capacitor, and then the electric field may collapse, and that gives back this energy back into the system. And the power company doesn't want this, or can't afford to have a lot of this energy being pushed back and forth in these energy storage elements without keeping track of it, because it's actually impacting their ability to deliver usable power in the form of average power. And because of that, we need to keep track of it. They do and we do. On our end, on the load side, we're probably trying to minimize the amount of extra energy that's being pushed back and forth to help with these energy storage devices of inductors and capacitors. And the power company is saying, wow, you're requiring me to produce more energy just so that or to use more energy so that I can now keep you supplied with the power, the workable power, the average power that you need. That now power that is being used by these inductors and capacitors is really orthogonal to the average real power, and because of that, we actually now give it a new name and keep track of it separate from the real power. We now have reactive power, and that will denote as Q, and in fact, it will be given the units of volt amperes reactive so that we can distinguish that between the watts of the useful power that is the real power that's helping us to drive machines or to move equipment, etc., that the power company is wanting to deliver to us. But because we have these inductive systems, maybe a bunch of big machines, we may want to be introducing some capacitor banks to try to get the sort of countering the effect of the magnetic fields. We may want the electric fields and the magnetic fields to be helping each other out on our load side. And so we are interested in, and so is the power company, this combination of real power and reactive power. And that now leads us to a notion of complex power. That's now where we're dealing with the real power. Orthogonal to that is the complex power, and I want us to be getting comfortable with right triangles again, back from our geometry days. And what we want to do is be able to understand, how do we work with complex power and effectively understand how to maybe reduce Q or make P more efficient in our problems that we're working with. That's in really a single phase, or I might say a one phase. That's chapter 10, which now that's maybe for smaller customers. If we're worried about moving larger amounts of power back and forth, then we step it up a notch, and now we introduce the concept of three-phase power. And here you could think of 3 coming in the form of A, B, and C. And now we have these 3 different phases, A, B, and C. And in chapter 11, which is where we start dealing with three-phase power, we'll concentrate on the condition where the A phase, the B phase, and the C phase are balanced. That now allows us to actually use the tools that we developed in chapter 10 to solve some of these problems. And in order to keep these balanced systems in play and to use our energy more efficiently, or to use the power more effectively, or to maybe use alternative energy sources in the form of solar or wind, now what we may want to do is be switching loads in, switching loads out, switching sources back and forth. All of that now involves changing from this sinusoidal steady state consistency that we maybe are using or assuming in chapters 10 and 11. Now what we may want to do is think about what happens when we do start having changes or switches involved. And when we start thinking about switches or initial conditions, meaning we're no longer thinking about things happening in the same way forever. We now have things changing on us. Once we have switching and initial conditions, we are introducing transient behavior into our system. And because of that, it would be nice if we could actually understand how to analyze this beyond what we've been doing up above. In chapters 10 and 11, we're dealing with complex numbers in the form of phasors, which have a magnitude and an angle. Now that we want to talk about transients or to consider DC circuits and sinusoidal steady state, or to be able to encompass those all with the same analysis techniques, what we want to do, so this was now phasors, which was a generalization of the DC circuit analysis. We want to generalize that even further to allow us to treat transients and initial conditions together. Now we open up a new analysis technique in the form of the Laplace transform. And this now allows us to incorporate, or allows transients and steady state type behavior to be analyzed in one swoop or together, so that now we can incorporate initial conditions, and as we introduce Laplace transforms, which will be in chapters 12 and 13, now we'll start being able to open up a lot more analysis techniques, and in fact we'll be able to start considering many more combinations of circuits or energy storage devices. We now are going to be worrying about more than just onesies and twosies. For our energy storage elements, where there I'm sort of lumping onesies and twosies, meaning one of our loads might have been the transmission line, a second might have been the loads. Now we want to consider more complicated interconnections, or now we have more inductors and capacitors available to us, and we may still want to think about those in one transfer function or one description from a source or input to an output. And for that, we will then introduce this concept of transfer functions as we're working through the ideas of Laplace transforms, where now we are going to be able to say, oh, we now have a complex frequency variable S. We'll have a relationship between the output, which we're denoting here as capital V sub 0 of S. Our system will be described by a transfer function, and we'll be dealing mostly with, if not exclusively, with single input and single output systems. But this transfer function now represents our system. And in this class, it most likely will be focusing on a circuit. Now we have this complicated circuit. We want to know from this source voltage, which might be labeled as capital V sub I of S, how do we now analyze that circuit in terms of the behavior at the output, and we'll then label the output as capital V sub 0 of S. We can not only think in terms of this mathematical description, but we can also translate that or rewrite that or re-represent that in a more graphical way in a block diagram description, which maybe provides a more intuitive notion of the input. It goes now through our system, or the system now processes that input to produce or generate an output. And this opens up a lot more opportunities for analysis and understanding of these electric circuits, which by analogy or by extension you can work in many other domains. But this now with the complex frequency variable S, we're working in the frequency domain. We'll also want to get comfortable going back and forth in terms of what's the time domain behavior of the system. And we can talk now about an impulse response, which is now going from the frequency domain or transfer function description of our system, capital H of S, through what we will now call an inverse Laplace transform to yield or to produce this impulse response. And now that's lowercase h of t. All of that said will allow us to hopefully become a little bit more comfortable, or yeah, comfortable is a good word, with this connection between the time domain description of our system, maybe the impulse response, and the frequency domain description, which is this transfer function. We also will then allow that, or that will now open up this ability or opportunity to talk about a frequency response, where now we might restrict our attention in this transfer function to just looking at the transfer function description as the complex frequency variable S is restricted to the imaginary axis, or when S is equal to j omega. That now gives us a frequency response description of our system, and that now becomes useful. We can now think about a frequency response, or the picture of that, a graphical description, is what we will term the Bode plot, which now gives us the magnitude and phase characteristics of our system. And that is where we will jump into the appendix, Appendix E, to talk about the Bode plot or frequency response behavior of a given system. Again, we'll be trying to become more comfortable with moving back and forth between frequency domain and time domain. What's happening in the frequency domain? It's sometimes nice to think about frequencies and frequency behavior of a circuit or system. It's also nice to think in terms of the time domain. And if we're looking at the time domain, we can look at generic output responses of a system by using the impulse response of the system, h of t, together with the time domain input, let's say lowercase v sub I of t, and that now, by combining those in a special way, which will be via a convolution integral, we'll be able to take this description of our system, which is how does the system respond to an impulse? That's the impulse response. We're not going to hit it with just an impulse, but in fact we may apply a generic input waveform. Let's say it's an input voltage. The convolution integral will now allow us to understand or generate or produce what the output of that system will actually be. And we can call that now the output response of a given system, which is now the convolution, which we now introduce this fancy star symbol. It's not multiplication, but now this particular symbol is the convolution. How do we now connect or utilize the impulse response together with this generic input v sub I to produce an output response? Where, to give us something to think about, suppose that we now applied a pulse waveform to a system. Let's say this is now our generic input. This is a time domain signal that we're interested in. We now we now have our input, generic input, v sub I of t, which is some amplitude for a given finite length of time. We now want to apply that to a system that in the time domain has an impulse response that maybe looks something like this, and we might like to know what's going to happen when we hit our system, which is governed by this impulse response behavior h of t with this particular input v sub I. What may actually happen is now we have an output that builds up and starts to look something like that pulse, but then it doesn't immediately turn off like the input. It now has more of a tail to it, and this is now our output due to that input. That's a way of thinking about the input-output behavior of a system, but that will open up the opportunity by thinking in the frequency domain. We'll also be able to talk about filters, which are a particular type of system, and we'll begin that discussion of filters by dealing with passive filters, which means that now we are simply looking at R's, L's, and C's, or combinations of those. This is now chapter 14 to allow us to build frequency selective filters. And a very fundamental passive filter is this classical combination of a resistor and capacitor, where the output voltage is across the capacitor, the input voltage is applied to the series combination of R and C. And in fact, this interconnected structure with this resistor and capacitor gives us a passive low-pass filter, which means if V sub I contains a noisy signal, maybe we can filter out that noise by pushing it through this passive low-pass filter, and that now is what will be the subject of chapter 14. And now that we have the tools of our Laplace transforms and transfer functions, we can find the transfer function between V sub I and V sub O, or we will now be able to determine how to design such a transfer function and relate that or connect that to this physical circuit of an RC system. Once we've understood a little bit better about this frequency selective behavior of systems, we can move into active filters. And now active filters means that we're dealing with operational amplifiers. We're now powering up some additional circuitry that we then interconnect around these op amps with R's and C's. And that allows us to have a little bit better ability to manipulate the frequency response of these filters, which means that maybe we can have, for the same bandwidth of response, here I'm trying to illustrate the magnitude response, and that's supposed to be a flat curve initially, and then it starts rolling off into the stop band. This is now our pass band. Over here, we're transitioning into the stop band, meaning filter or frequencies beyond omega sub b we're trying to minimize in the output, and the frequencies in the pass band or below omega sub b we're trying to pass through that system. And that's the topic of chapter 15, which is dealing with active filters. Now that we have active filters, passive filters, this idea of systems, we can generalize that even further and start talking about two-port networks, which is the material in chapter 18. Now we will have something that we will have available to us or we will need to design, that's this cloud symbol inside this box, but we have some input terminals, which maybe we have a voltage V1, maybe we have a current I1 and a current I1 satisfying the port requirement. Here's our voltage V2 and the appropriate current. Now we can use these descriptions of two-port networks. It's, I hope, clear that we have two ports. We have an input port and an output port. And with this terminology or with these definitions, we are now able to use this to describe different electronics. We could even see this applied in an electromagnetics setting. And that now opens the opportunity for us to analyze or use the techniques that we'll be learning in this class to move into many other disciplines or sub-disciplines, not only in electrical engineering, but in other engineering fields. If time permits, we'll talk about then the material of Chapter 16, which now allows us to use again another frequency domain concept, which is dealing with periodic waveforms or general periodic waveforms. Again, this is now going back into Chapter 16. We could think of not just sinusoidal steady state waveforms, but now we have a more general periodic waveform. These are supposed to be the same little bumps that maybe have some shape to them. We can now identify a fundamental period associated with that waveform. Here, let's say this is V sub I of t. We can now, via using Chapter 16 techniques, talk about how do we now find a sinusoidal waveform description of this general periodic signal, because we now know, based on what we've been using or learning in previous parts of this class, how a sinusoid will be manipulated or adjusted by the system in question. And using Fourier Series, we'll learn how to build or identify, with respect to a general periodic waveform, the combination of sines and cosines that allow us to recreate or subpartition this periodic waveform into a collection, which can be an infinite collection of sines and cosines, where you can see in this description we're identifying a particular frequency, omega naught, or the fundamental frequency, omega naught, which is 2 pi f naught, which in fact is related to that fundamental period up above, capital T. Once we have this, and as I said, we'll be comfortable with analyzing how a system performs or behaves relative to sinusoidal excitations, we can now combine these concepts. We can combine the concept of a Fourier series representation of a periodic waveform. So we now have a Fourier series of V sub I of t. We can now say, how is a particular system or with a circuit that has a given transfer function h of s, what's going to happen to the output of that when the system is excited by the input V sub I of t, which is some general periodic waveform. So we are wanting to be able to find the output given V sub I of t and the transfer function h of s. Again, we can now go back to this understanding of this relationship between our input signal in the time domain given by v sub I of t, the system that we now are exciting with that input signal to produce an output signal in the time domain v sub 0 of t. We can use the notion of the Fourier series to identify what's happening in the frequency domain with this periodic waveform. We know how to describe the system in terms of its magnitude response and its phase response. That's the frequency response of this system as a function of omega, where this is now omega. And that's now going to, in combination with the Fourier series of our input, where the input now might have a magnitude description, maybe it has a particular magnitude at the fundamental frequency, then the Fourier series will allow us to find what's happening at each of these higher harmonics in terms of frequency, in terms of its magnitude and angle. Etc. We can then combine how these sinusoids are passed or influenced by the system, the frequency response, to produce the ultimate, or the output, which is now a combination, because we're dealing with linear systems, a combination of how the system itself behaves at each of these frequencies, omega 0 to omega 0, that I'm representing as omega sub I. That will now scale, so now we have this times the magnitude of v sub I cosine of I omega naught t. I is not the square root of -1, that's just now an index on our infinite sum, will be operating at the fundamental omega naught and its harmonics 2 omega naught, 3 omega naught. And then I've run out of room here, but this will now be plus in the argument of the cosine, the angle of v sub I and the angle introduced by the transfer function h of j omega sub I. And that now is how we will be able to combine all of this material from the contents of chapters 10 up through chapter 16 and on into 18, this notion of analyzing a system based on the transfer function of our circuit, a generic input, and producing a given output. And all of that now you want to be tying together as a result of this particular class.